From the bridge you drove over this morning to the phone that's probably in your hand right now, we are literally surrounded by things we trust to just work. But have you ever stopped to wonder how engineers can be so sure? Today, we're going to dive into that, into the fundamental battle between stress and strength that decides if something holds together or if it fails, sometimes catastrophically. So it all boils down to this question. How do we know something is strong enough? And look, on the surface, that sounds pretty simple, right? But for an engineer, this is one of the biggest, most critical challenges they face. Answering it isn't a hunch, it's not guesswork. It's a really deep mathematical quest to find some kind of certainty in a world that is, by its very nature, totally uncertain. Okay, so at the very heart of this entire field, you've got this constant conflict. It's like a war that's always being fought between two opposing forces. And understanding this battle, that's the absolute first step to getting what makes something truly reliable. And it really breaks down to this. You've got stress, which is basically everything the outside world throws at an object. Think about the weight of cars on a bridge or the wind pushing on a skyscraper. Then on the other side, you've got strength. That's the material's own internal power to just say nope and push back. Every single part of every single thing we build is living in this constant state of tension. So if you're an engineer faced with this constant battle, you need a way to predict the winner, right? Well, that need led them to create the very first blueprint for predicting safety. And we call it the classic model. And here it is, the stress-strength interference model. Now, the key thing to get here, the real light bulb moment, is that this isn't about absolutes. It's all about probability. See, engineers figured out pretty quickly that neither stress nor strength is just one single perfect number. They change, they vary. So this model was built to embrace that uncertainty and use it to actually calculate the risk. In other words, this completely changes the question we're asking. We're not asking, is it strong enough anymore? Instead, we have to ask, what are the chances it's strong enough? Suddenly, reliability becomes a number, a percentage. It's a concrete way to measure just how confident we are that strength is going to win this fight. So how does it actually work? Well, the model looks at both stress and strength as statistical distributions. Just picture two bell curves. Now, where those two curves overlap or interfere, well, that's the danger zone. That's where failure can happen. By calculating the size of that overlap, engineers can literally predict the probability of failure. And that number informs everything from what materials to use to how to design the part, especially for components that aren't moving around a lot, what we call static loads. But, of course, the world is rarely that simple. It's not usually made of single, isolated parts. And this is where that classic model starts to show its age, and where reality forces us to get way, way more sophisticated. I mean, just think about an airplane wing for a second, or the entire power grid. In systems like these, the failure of one tiny little part can set off a domino effect, a cascade that brings the whole thing down. A model that only looks at one component in a vacuum is going to miss that bigger, scarier picture. And this is where you see the huge leap in complexity. Look, it's one thing to analyze a single bolt. It's a whole other thing to analyze all 1,000 bolts in a big structure. But the real quantum leap, the thing that makes this so hard, is understanding how the stress on bolt number 1 might change the strength of bolt number 572 down the line. That interconnectedness, that dependency, is the puzzle of modern reliability engineering. So, to tackle this, engineers had to bring in the big guns. They use this powerful statistical tool called a copula function. It sounds complicated, but think of it like this. Instead of just predicting the chance of rain, and separately the chance of high winds, a copula helps you predict the chance of them happening together at the same time. It's a tool specifically designed to map out those complex connections, letting us see a system for what it is, not just a pile of parts, but an interconnected web. And on top of that, things in the real world rarely just go from perfect to broken in an instant, right? They wear down, they get old, they degrade. So modern models have to account for this progressive failure. By tracking that slow decay over time, we can actually predict when a partial failure might pop up, and then we can schedule maintenance before it turns into a total system failure. It's all about being proactive instead of just reactive. But, even with all these advanced tools, engineers are constantly being pushed by brand new challenges. So let's take a look at the modern frontier, where this quest for certainty is, well, tougher than it's ever been. First up, multi-axial stress. In a textbook, a force is this nice, clean arrow pushing in one direction. But in the real world, no way. A part in a jet engine is getting pulled, pushed, twisted, and bent from multiple directions all at once. That's multi-axial stress, and trying to model that is exponentially harder than a simple one-way force. Next, the environment itself is an active player in this battle. It's not just a backdrop. Humidity causes rust, salt water causes corrosion, extreme temperatures can cause cracking. This means a material's strength isn't some fixed number you can look up in a book. It's a moving target that's constantly changing. And that just adds another really complex layer of uncertainty to the whole thing. And finally, the very stuff we're building with is getting more and more complex. I mean, we're not just using solid chunks of steel anymore. We're talking about advanced composites or even natural materials like rock and soil, which are filled with tiny pores and internal weak spots. The old models, the ones designed for solid metal, just can't predict how these new materials might fail. So where do we possibly go from here? With all these new challenges, what's the solution? Well, as the source material for this explainer points out, a lot of researchers are now turning to artificial intelligence. The big hope is that AI can crunch massive amounts of data and find hidden patterns in these incredibly complex problems, basically bridging the gaps where our current models just fall short. So what this really all means is that this problem is far from solved. I mean, from the simplest little bolts to the most complex global systems, this quest for reliability is a journey that really never ends. Every time our technology gets more advanced, the science of keeping it safe has to get more advanced right alongside it. And that leaves us with one final, pretty critical thought to chew on. We're building things like self-driving cars, reusable rockets, and global digital networks, systems that are way more complex than anything in human history. The question isn't just how we make them work, it's how we make them fundamentally trustworthy. AI is definitely one piece of the puzzle, but what comes next? What's the next great idea that's going to ensure our future is not just innovative, but also safe?